metric-Palatini theory. Okay. This theory is based on is essentially outlined in this book that was published with Tiberi Harker back in 2018. If you want to know more information, it's there. And so a brief outline of the talk. So there's a need for new gravitational physics, and I'll also be speaking about the foundations of gravitation, and of course going beyond GR, which is modified gravity. There's been a lot of talks yesterday also, and there'll be more talks today and also until the final day on Thursday. And I'll just mention a few extensions of FFR and some applications, and of course that the main theme of this focused talk will be about the hybrid metric-Palatini theory. I'll be speaking a bit about the cosmology, the weak fields regime, also a bit about the astrophysical applications, and also a bit about the gravitational waves, and also how to construct these theories, right? Because they also consist of a new building block. So I'll be speaking a bit about a more generalized theory, so you can have a feeling of how one can construct these theories, and also see what are the advantages and also the well, pros and cons, right? The disadvantages of the theory. Some of them are plagued with ghosts and instabilities. Well, we all know that the fact of the late-time cosmic acceleration has forced theoreticians and experimentalists to pose a question: is GR the correct relativistic theory of gravitation? And indeed, the fact that GR is facing so many challenges, as in the difficulty in explaining particular observations like the late-time cosmic acceleration, and also the incompatibility with other well-established theories as quantum mechanics, and also the lack of uniqueness. There's many theories that one can build that also take into account the observations that we use, and that GR is very successful for in the weak field regime, at least. So all this, is this indicative of a need for new gravitational physics? So this is the big question, okay? And of course, cosmology is also an ideal testing ground for GR, and especially for the late-time cosmic acceleration. And a promising approach is to assume that at large scales, GR breaks down and a more general action describes the gravitational field. This is also spoken about yesterday. And we do have the so-called generalizations or extensions of the Einstein-Hilbert-Lagrangian. One can extend these theories if you consider, for instance, the early universe inflation, where when there's high curvatures, when one can consider an R squared term which dominates over the R. One can also take into account invariance, the Ritchie, the Riemann, and the Weil, and etc. So this is also spoken a bit about yesterday, and also in the future talks. So there's a whole plethora of theories that one can build, okay? And also there's also physical motivations for these modifications of gravity, especially for the possibility of a more realistic representation of the gravitational fields near curvature singularities, and also to create some first-order approximation for the quantum theory of gravitational fields. We know that GR, of course, is a classical theory, so there's no reference to an action is really needed. But the Lagrangian formulation is really elegant and it has its merits. So at least at the quantum level, the action acquires a physical meaning, and a more fundamental theory of gravity will provide an effective gravitational action at a suitable limit. It's also easier to compare the alternative gravitational theories through the actions rather than by the field equations. The field equations, as you well know, some of them are really messy, and one cannot build any physical insight. Insights, and one has a better grasp of the physics through the action, especially through the couplings, the kinetic and the dynamical terms, etc. So, for instance, if you consider FFR, it's really has an appealing feature. It combines mathematical simplicity and has a fair amount of generality. The richest scalar is a dynamical degree of freedom, as one can see through the trace equation. So it also introduces a new light scalar degree of freedom. Okay, this does produce the late-time cosmic acceleration, but the light scalar strongly violates the solar system constraints. Okay, so this was really, really a big issue about 14 years ago in 2007. I remember when people started really going into the weak field limits, and there was papers coming out where they considered that the ppm gamma perimeter was 1/2, and then one read the paper and there was no error in fact, and then a week later there was a new paper coming out where they said that gamma was equal to 1, and there was a big confusion back then. And but now we know that the way out is through this so-called chameleon mechanism. That is, the scalar field does become massive in the solar system. So just to give a very pedagogical outline of this, there's one can take into account several approaches: the so-called metric, the Palatini, the so-called also metric affine formalisms. With a metric formalism, I'm sure that you all know, just to remind you that the fundamental field is the metric. The Palatini formalism, one has the connection as the fundamental field. The so-called metric affine formalisms is when the matter-Lagrangian also couples to the connection, not only to the metric. I would say that there's also a fourth approach, which takes into account the metric and the Palatini formalism. And this is the so-called hybrid metric-Palatini formalism, which I will be describing now. Okay, so the action is given by equation 3. So we see that we have the Einstein-Hilbert term first, and then it's extended by an f of r. The second f of r, this r term is the so-called Palatini curvature. So where the first r is the metric curvature. So this new r, this curly r, this Palatini curvature is defined in terms of an independent connection, okay, which is, yeah, I'm not sure that if you can see my cursor, where the Ricci tensor is given in terms of this new independent connection, okay. So there's a few reviews over here that if you're interested, you can take into account. So this is quite interesting. So we started trying to see exactly what were the implications of taking into account this mixture of the metric and the Palatini formalism, and because both do possess some severe drawbacks, okay. And so the first motivation was to see exactly what would happen, okay, at least at the weak field limit, and also in cosmology, if one took into account the mixture, the hybrid approach. And the question that we posed back then in 2011 was, do these severe drawbacks still appear in this theory? And the question is no, as you will see in a while. So varying the action, this action 3, okay, we have this field equation, and we take into account the energy momentum tensor is defined as usual by equation 5, and also varying the action with respect to this new connection, okay, gives you this equation of motion given by equation 6, and it does imply that this new connection, okay, is the Leverage-Vito connection of a new metric, okay, given in terms of the physical metric and a conformal factor. I'll be calling the G mu the physical metric because that's the one that's the matter-Lagrangian couples to, okay. So it's one can work in this curvature, approach, but it's really simpler if you go to the scalar tensor representation, and that theory that I just showed you, that the action can also be represented by equation 7. Okay, so people working with the Brown-Sticky theory will say, okay, well, this is very similar to what we do in Brown-Sticky, when you take into account that the omega, the Brown-Sticky perimeter, is equal to minus 3/2. But there's a big difference here because there's a new coupling to the R. Okay, so with the Brown-Sticky theory, we take into account the omega is equal to -3. There's the R is just coupled to the scalar field. Okay, and this makes all the difference, as you will see. Let me remind you that if you take into account the f of r theory, the metric approach, okay, into a Brown-Sticky theory, it gives you a Brown-Sticky perimeter where it's 0. And if you take into account the Palatini formalism, it'll give you a Brown-Sticky theory where the Brown-Sticky perimeter is equal to -3/2. Okay, so this is really interesting. And it has a few novelties, which is really really interesting in our point of view. Okay, so the gravitational field equation is given by equation 8. Okay, so to give you an idea, it's very similar to the Brown-Sticky theory, but there's different couplings, of course, that appear. And of course, we can see that space-time curvature is also generated by both the matter and also by the steady field. Okay. So if you do prefer working in the Einstein frame, one can do this transformation, this conformal transformation given by equation 9, where the Einstein frame Lagrangian takes the form of equation 10, and you can also put it into its canonical form by rescaling the steady field. Okay, so if you prefer working in the Einstein frame. So when you come up with these new theories, it's also very important to see exactly what the weak field slow motion behavior is of these theories. So I'll just give you a very brief review of what we found. So we have here this effective Newton constant, and what is interesting is this post-Newtonian perimeter, the gamma. Okay, so can't seem to. Okay, there we are. So it's clear that the coupling of the scalar field to the local system depends on the amplitude, okay, of this scalar field, okay. And if the amplitude is very small, then we see that the effective G is equal to the Newtonian constant, and what is also important is that the gamma is equal to 1. Okay, so this is really different to what happens in the f of r metric formalism. Let me just show you what happens in the metric formalism of f of r. Here we have the gamma, okay, and the gamma is equal to equation 16, and it's equal to 1 when we take into account a large effective mass, to make the Yukawa type corrections negligible in local experiments. So this is basically what you do with the chameleon mechanism. Okay, so for the metric f of r theory, gravitational theory, okay, I mean, one needs the so-called chameleon mechanism to make these theories viable. Okay, and we were really excited when we found that with the hybrid theory, there's two mechanisms. So independent of the mass, okay, we can just consider a very small amplitude, background amplitude, which gives you gamma is equal to 1, independent of the mass. So you don't. So for this regime, one can evade completely the chameleon mechanism, and that's motivated us to go further into this theory. So the next question is that, okay, so this does pass the local tests, okay, the weak field tests. If the background amplitude is very small, what happens with cosmology? Okay, so a very simple model. Just consider the Friedmann-Lemaitre, Robertson-Walker metric, a flat one. And to give you an idea of the field equations, people working with this will see that it's very similar to the Brown-Sticky theory, with the omega is equal to -3/2, but there's different couplings over here, okay? And the scalar field equation is given by equation 19. Also, there's a few differences, okay? So that gives you different dynamics as well. For simplicity, just to give you an idea, let's consider a very simple model, okay, a quadratic potential. So we verify that the trace of the field equation automatically implies this, okay, r is equal to, so the r is proportional to the trace of the energy momentum tensor, and also this v0 that appears in the potential. So as with cosmic expansion, we know that the trace goes to 0. So this does naturally evolve into a de Sitter phase, okay, where the potential will be proportional to the cosmological constant, which is also consistent with observations. If V1 is positive, okay, then the de Sitter regime also represents the minimum of the potential. And the effective mass for the local experiments, given by this, is also positive if we take into account this restriction. For V1 much greater than V0, the amplitude is small enough to pass these solar system tests. So the exact de Sitter solution is compatible with the dynamics of the scalar field in this model. So this is also very promising. I mean, seeing that a very simple model, this quadratic model given by equation 20, also gives you this late time cosmic acceleration with an effective lambda. If you want to do more cosmology, of course, you have to go, you have to do, well, perturbation theory. And of course, to understand the cosmological structure formation, we also deduce the perturbation equations and also analyze them for specific cases. And this does pave the way for a detailed comparison of the predictions with the cosmological data on large-scale structure and the cosmic microwave background. To give you an idea, we consider the Newtonian gauge, which can be parameterized by these two gravitational potentials given by equation 21. And we also consider a matter source with a perfect fluid with a background equation of state omega. And we have this, the density perturbation given by delta P rho m and over rho m. And we also have the pressure perturbation and the velocity. And we show that both potentials are given by equation 22, okay? So if you assume a perfect fluid, the continuity and the oil equations for the matter content are given by equations 23 and 24. This is also to give you an idea, respectively, and also the linear part of the Klein-Gordon equation will be given by 25. Taking into account all this analysis, one can also consider the structure formation in the matter-dominated universe, okay? So we assume that scales deep inside the Hubble radius, okay? So it's the so-called quasi-static approximation. Combining the continuity and the oil equations given before in this approximation, we have finally this perturbation equation given by equation 26, where we have this effective G, and we see also that it depends on this background value of the scalar field. And note that if it's very small, taking into account these solar system tests, okay, so we do expect that the growth of structure will be very similar to GR, and that is what we found. In fact, I won't show you the results. Okay, so if you also well, consider the vacuum fluctuations, of course, the propagation of the scalar degree of freedom in vacuum is also very crucial to check the consistency of the theory. Take into account vacuum, and if you consider the curvature perturbation in the uniform field gauge, zeta. So we have here, in terms of the Newtonian gauge perturbation, it's given by equation 28, okay, these two potentials. And we obtain the evolution equation given by equation 29, which is really tedious. And this does give you, this does generate the fluctuations for the hybrid gravity inflation. Okay, and we can also, well, you do this in the Einstein frame, which is probably neater and probably more intuitive. Okay, so let me just show you what one can do further. Okay, I'm trying to give you a very brief pedagogical outline of this theory, but as we have new building blocks, okay, so this theory is has a space which is really large, okay, because in addition to the metric and the Sevich connection, one has this additional independent connection, okay, which can be used as a building block to construct further curvature invariants. And one can take all these curvature invariants given by equation 30, okay? So we have here the Palatini curvatures, hybrids, the Riemanns, and one can just, play around with this, and it's really, it's nice to play with this, but it's really cumbersome going through all these calculations by brute force. So we haven't performed these theories, but we have really taken into account the Graviton propagator to try to understand the instabilities that do appear, taking into account a higher order hybrid theory, okay? So let's consider this theory, okay, given by equation 31, given by the action. We have here the metric curvature, we have the Palatini curvature, and we have this new contraction over here, which is a contraction of a mixture of the metric and the hybrid Ricci curvature. All right, so this is quite a representative class of the more general theories, and it will also give you an idea of the instabilities that appear, and also how one can further build these theories. Okay, take into account this action, one can deduce the field equations, which are very messy, and of course take into account the variation with respect to the new connection that gives you That's the connection is also dictated by a Leverage-Vita connection of a new auxiliary metric given by this relationship over here, okay, where the R and the G is given by these linear combinations. So, like I mentioned, if you want to verify exactly what happens with the instabilities, one can go through brute force theory by theory, but it's also very intuitive and very pedagogical to take into account the Graviton propagator. So if you consider perturbations, okay, around Minkowski space, and in inverting the linearized field equations for the physical metric, this provides the propagators for the Graviton and also additional degrees of freedom that may be present in the perturbed metric. So the propagator is given by equation 33, where this term over here on the right-hand side represents the linearized stress energy source. So in the formalism of the spin projector operators, the result can be given in Fourier space in terms of two functions, A and C. We have here these functions in terms of the operators. I'll show you exactly what the forms are. And we have here this first term, okay, picks up the spin 2, and this P0 picks up the scalar modes of the fluctuations, okay. So the A and the B are quite messy, in fact. And while defining a new A and B, capital A and capital B given in terms of these quantities, taking into account this theory, okay, and we verify that the two functions are given by equation 36 and 37. So this is really interesting because now one can just verify exactly if we have the right intuition, taking into account theories that we know already. So, for instance, if you take into account the pure metric case, okay, where we have this condition, we have A, the Graviton propagator gives you equation 38, okay? So you have the GR term, and we also have an extra scalar degree of freedom, as was expected, since the FFR models are known to be equivalent to Bronsted-Key theories with a variation parameter, as I mentioned before. So the mass of the scalaron, okay, is given by this quantity over here. And as long as this is positive, the theory is stable. Otherwise, we have a tachyonic mass, which spoils the stability around Minkowski space. So this is really known, okay? So as a first intuition, as a first application of this formalism, we have the right intuitions and we also have the right results. What about Palatini, the pure Palatini FFR? So as I mentioned before, it's equivalent to a Bronsted-Key theory with the perimeter, Bronsted perimeter is equal to -3/2. So this value, well, does correspond to a vanishing kinetic term of the field. And so it's non-dynamical, okay? So therefore, we expect that no additional scalar degree of freedom should appear, okay? That's our first physical intuition. And taking into account the formalism which I presented, this does indeed correspond to what we would expect, okay? So the modes, the propagated modes are equal to GR. For the hybrid metric-Palatini models, also take into account some intuition. So in Ricci flat spacetimes, the hybrid metric-Palatini theories also share the properties of the Palatini FFR theories, which in vacuum reduce to GR with a positive cosmological constant. So therefore, one should also expect that the modes should also correspond to GR, and that's exactly what we have, okay? So our physical intuition is also in agreement with what we have deduced. Now, taking into account a more complicated theory, so you can see exactly why we shouldn't really go into these theories by brute force. If you arrange the propagator, we have this formula given by equation 41. And we can see that we have a modulated Graviton propagator, which adds 2 extra poles, okay, which you can see in these quantities. In addition, there also appears a scalar propagator that has 5 poles, okay? And so this theory is seriously haunted by ghosts, and one can consider not to be physical, of course. So it's easy to convince oneself that this does occur very generically once one builds the action from a higher order hybrid curvature invariance. And this is also very, very pedagogical, and also as a warning not to go into high order, because well, if you want to, one can also cure these instabilities, of course. But this is a warning sign, okay? If you do to really well, beware of these more complicated theories. Okay, so let me just see the time. I have some time, but I'm also finishing in a little while. So I've tried to give you a pedagogical approach for the weak field and the cosmology, and also through the building blocks of these new theories. And one can also take into account dark matter. One can consider that dark matter is also mimicked by modified gravity. Quite a lot of work has been done here, and especially with the hybrid metric-Palatini theory. So back in 2013, we had 2 papers out also that's considered that the virial theorem could also be explained by modified gravity in terms of this hybrid theory. So it's also quite intuitive, because the virial theorem gives you the excess mass, right, which can, if you rearrange your gravitational field equations, you have these higher order curvature terms, which can mimic this extra mass. Okay, so one can use the so-called generalized virial theorem to explain the dark matter problem, and also the galactic rotation curves in hybrid metric-Palatini theory. So it's also very intuitive and also very pedagogical, how one can also mimic these flat rotation curves. Okay, so oops, sorry about that. More recent work, a lot of applications have been done, especially with compact objects like hybrid stars, given in this fourth reference, and wormhole geometries, and also vacuum solutions, black hole solutions can also be found, which is extremely difficult to find, especially exact solutions. So we did a lot of numerics, and also cosmic strings solutions were also found. We also went into a generalized theory. This is given as a PhD working plan of Jean-Louis Rosa, and he did some great work. A lot of solutions were also found. Thick brain structures were also found in this generalized theory. The cosmological solutions were also found, and a few other solutions, such as wormhole stars and also black hole solutions, were also found. So it's quite a lot of applications that one can still do, and have already been done. Nice work also by Paulo Sá, has also worked with this generalized theory. Okay, and he's managed to unify the description of dark energy and dark matter within this theory, and also a triple unification of inflation, dark energy, and dark matter, given into account these 2 scalar fields. So if you take into account this theory, we have 2 degrees of freedom, which if you go to a Scalar-tensor representation, you have 2 scalar fields. Okay, 2 degrees of freedom. So nice work by Paulo Sá. As a summary, I've presented a hybrid metric-Palatini framework for the theories of gravity, and tested the new theories it entails using a number of theoretical consistency checks and also observational constraints. Also interesting, and this is it's what really motivated us to go further into this theory. It's that it may evade altogether the so-called chameleon mechanism, okay, which is quite contrived if you, well, depending of course on one's point of view. It's one also excludes theory inhabited by ghost-like superluminal propagating degrees of freedom, and also otherwise pathological degrees of freedom. So in a more holistic view of physics, one would expect nature to make somehow a choice between the 2 distinctions, okay? That is offered by the metric and the Palatini formalisms. So this does take you back into the foundations of these gravitational theories, which is the fundamental field. Is it the metric? Is it the Palatini? So this is a big debate going on. And so if you take into account that both fields are fundamental, okay, the metric, which gives you the distances and times, and the connection, which gives you the parallel transport, and etc. It's been shown. Well, we showed that the theory is also consistent with observations, and does combine elements of these 2 approaches, and it's possible to do this. So maybe gravity admits a diffuse formulation where a mixture of both formalisms allow to successively address large classes of these phenomena. Okay, Just as an outlook and to finalize, the tests from the solar system, the large-scale structure and lensing essentially restrict the range of allowed modified theories of gravity. And we know, of course, that surveys as the Euclid, which will be launched very soon, and the SKA, there will be a few talks in this conference on that. And so all these new missions, will also provide new opportunities to test the different cosmological models, which is also fascinating. Of course, indeed, with the wealth of unprecedented high precision observational data that will become available by these upcoming and planned surveys, we are dawning probably in a new golden age. Yesterday, George Ellis spoke of the golden age of GR back in the 70s and 60s. But probably we're also dawning into a golden age of cosmology, which offers a window into the understanding the perplexing nature of the cosmic acceleration, dark matter, and of course, gravity itself. So thank you very much for your attention.